So good day. Today we're gonna discuss about thermal conduction. So first, let us define what is thermal conduction. So thermal conduction is how heat energy flows from a hot to cold region of a substance without the molecules of the substance moving from the hot to cold region. So in heat transfer, it is a golden rule that heat always flows from hot to cold. So conductivity by molecules. Molecules vibrate more when they are heated. Intermolecular forces allow their molecules to pass their vibrations from one to another, thus conducting the heat. Because when molecules are heated, they vibrate and they send their vibrations to their adjacent molecules. So the stronger the forces, the faster the vibrations are passed. And then the solids, therefore, are the best conductors and gases are the worst. Since gases have separate molecules, the vibration is very hard to transfer. A very poor conductor is called an insulator, and a vacuum does not allow conduction. So next is conduction through metals. Metals have an additional method of conduction. Metals have electrons that can move from one atom to another. These free electrons can pass energy through the metal very quickly, and most of the best conductors are metals. However, diamond, a non-metal, is the best conductor despite only using the molecule-to-molecule method, because diamond is a very compressed mineral. It is compressed carbon. That's why its molecules are so attached together that they transfer the vibrations more quickly. And also other crystals like salt, those that have crystallized structure can be the best conductors like salt and diamonds. So next is finding the best conductor. So here is a test to find the best conductor, where all of the rods have the same length and cross-sectional area. And these are the sample rods: the copper rod, the iron rod, the aluminum rod, and then the brass rod. And to test which one is the best conductor. So next, they are all heated equally at one end with a Bunsen burner. Then when the other end of a rod reaches a certain temperature, the paraffin wax as shown in the figure melts and the matchstick falls off. A matchstick will fall off the best conductor first. So the first matchstick to fall, that would be the best conductor. And then this should be the rod made of copper, because copper is the best conductor among all of them. So next is comparing brass and wood. The gummed paper singes and burns first on the wood side of the rod. This is because the brass removes heat away from the paper more quickly than the wood. Brass is therefore the better conductor than wood. So next, a test to prove that water is a poor conductor. A boiling tube of water is heated near the top of the water. The water boils at the top, while the bottom of the tube remains cool enough to hold. This shows that water and glass only conduct heat relatively slow. So water is a very slow conductor. So next is air is a good insulator. Air trapped in feathers, cavity, and wall insulations, loft insulation, duvets, and lagging greatly reduces heat loss by conduction. So just like how furry animals survive the cold in the Arctic, this is the way that they provide insulation from the cold. So next is formulas for solving for conduction. For the walls, as you can see here, the heat transferred is equals to the conductance, coefficient of conductance, times the area, times the delta T or TA minus TB over the thickness of the wall, of the material. So these other formulas are just derived from the original formula based on their circumstances. So next is for pipes. So for the pipe, since it is a pipe, we will use the cylindrical formula for area. And then the length for the, for the area. We will use the length for the area. And then for the thickness, we will use ln of the inner radius over the outer radius. Oh no, the outer radius over the inner radius. So, just the same from, it was just derived, just like I said. So, next is for the fluids. So, fluids has already given the surface conductance. So, fluids already have surface conductance. We just put it in the formula, which is the conductance times area times the difference in temperature. So here is the sample problem. So two metals have the same size but different type. The thermal conductivity of P is 2 times the thermal conductivity of Q. What is the temperature between the two metals, as shown in the figure below? So as seen in the problem, we can conclude that since they are in contact with each other, we can conclude that Q of the material P is equals to the heat transfer of the material Q, the metal Q. So we will expand this into the formula for conductance. So the formula for conductance is equals to the thermal conductance times the area times the temperature difference over the thickness of the material. So as we know that P, given from the figure, that P is twice as the thermal conductance of P is twice as the thermal conductance of Q. So we'll put 2 here. So we'll put the same here, which is the thermal conductance times area times the temperature difference over the thickness. So as we know, both plates have the same size, so we can cancel out the area and the thickness. So we will expand this, so we will get 2K times, so as we see in the figure, it is from 90 to minus the temperature in the between is equals to K times the temperature in between minus 0 degrees Celsius. So solve for T. We can cancel out the K since both are the same. It's just twice. So we will solve for the temperature. So we get 90 times 2, which is equals to 180 minus 2T is equals to T minus 0 is equals to T. So we transpose. We get 180 is equals to 2T becomes positive, so it becomes 3T. So divide both sides by 3, cancel, so we get T is equals to 60 degrees Celsius. So to check for the correct answer, so we got the correct answer. So next problem is metal rods of the same size but made of different metals are combined as shown in the figure below. If the thermal conductivity of metal 1 is 4 times the metal conductivity of 2, then what is then the temperature at the junction of the two metals? So as we see in the figure, both have the same size but different materials. Same problem, almost same problem as the earlier problem. So we can conclude that Q of metal 1 is equals to the heat transfer of metal 2. So we will expand this. We get the thermal conductance of metal 1 and then times the area times the temperature difference over the thickness of the rod, which is X times is equals to, but since we know that the conductivity of metal 1 is 4 times the conductivity of metal 2, then we get to put 4 here for the conductance of metal 1. So next is we put the formula for the heat transfer for metal 2. So which is the conductance times area of surface area times the difference in temperature over the thickness of the pipe. So we can, since they are the same size, we can cancel the area and then the thickness. And then also the conductivity, since it is just multiplied by 4 here, so we can cancel the conductivity. So we are left with 4 times the delta T, which is from 50 degrees Celsius minus the temperature in between, is equals to temperature in between minus 0 degrees Celsius, which is the temperature on the other end. So we solve for T, we multiply, so 200 minus 4T is equals to T minus 0 is equals to T. So transfer, this becomes positive, so 200 is equals to 5T. We add T plus 4T, so we divide by 5, so we get T is equals to 40 degrees Celsius. So to check for the answer, we got the correct answer. So that's it, and thank you for watching the video.